Hello everybody. In this video we're gonna start talking about the second part of this chapter, which is focusing on the diffusion coefficient or the diffusivity, and on the equations that we can use to predict the value of the diffusion coefficient for specific systems. Just to make things clearer for what we're gonna see in this video and the coming videos, we're gonna be talking about just some equations, mainly equations that we can use to predict the value of the diffusion coefficients. These equations are gonna be more of direct substitution, so you need to just get some data from tables, or there are some correlations that you can use to get some data, and from this data you can calculate the diffusion coefficient. So this is not going to be something that's difficult or tricky. It's simple, straightforward, and you just follow the steps. So it's not a tricky thing. But the thing that I want to emphasize, and I would like the audiences to keep in mind, is that there are some information that you can get out of this, and this for me is the most important message that you can take out of these. At the end of the day, these equations are going to be available. You can find them in the textbook, or you can find them in papers, or whatever the place that you can find these informations in, and you can find them. But the point that you can make better use of is to understand well the influence of each parameter on the diffusion coefficient. So it's important to notice how the temperature, the pressure, how the properties of the species and the properties of the environment are affecting the diffusion coefficient. And this for me is the most important message that you'll take. Again, everything is available. You can find all the informations and you can substitute, but these are the important information that you need to keep in your mind. So before talking about these, we just need to talk a little bit about the diffusion coefficient from the dimensions or the units point of view. So the equation, fixed law equation, states that the diffusion coefficient multiplied by the gradient of the concentration equals the flux. From this we can predict or can deduce the units of the diffusion coefficient. We know the flux is in gram moles per meter square second, or per gram if it is in mass units, and the concentration is mole or gram per meter cube, and the Z is in meters. So by cancelling out the similar terms, we will end up with the units of meter square per second, or it has the dimensions of L power 2 T power minus 1. So we usually use the units of meter square per second or centimeter square per second. And centimeter square per second is more common than the meter square per second, because centimeter square per second will have higher value than meter square per second. I mean the value of the number itself. It's not the value of the diffusion coefficient. So from what we will see later and from the simple logic, we can predict that the diffusion coefficient will be a function of the pressure, the temperature, and the concentration of the species, the medium, in the medium that it's diffusing in. And it's also a function of the properties of the two species, A and B, the medium and the diffusing species. This is something that we will see in the equations in more details, and we will get more information about them. But the point that we need to know now is that the diffusion coefficient, as we said before, it is an indication of how easy or hard the diffusion process is. So if the diffusion coefficient is high, the value of the diffusion coefficient is high, then the flux will be high, and then the rate of mass transfer is high, which means that the diffusion is easy and is quick, and vice versa. So as anybody would expect, in gas phase the diffusion is easier, since we have a lot of intermolecular spaces, and the molecules there are a lot of space in the molecules to diffuse through, which is larger than what you will find in liquid phase, and of course larger than what you'll find in the solid phase. And that's why we have some estimation of the values or a range of the values of the diffusion coefficient in gas phase, which would be 10 power minus 5 to 10 power minus 6 meters square per second. If you want to use centimeter square per second, then you multiply this by 10 power 4. So it's going to be 10 power minus 1 to 10 power minus 2 centimeters square per second. If in liquid phase, it's going to be 10 power minus 9 to 10 power minus 10, and in solid phase, it's 10 power minus 10 to 10 power minus 14. So you can see it is like a huge difference between gases and solids. It's a very, very, very big difference, which is expected from the properties of the two media. And now there is a question that we want to ask, and this is gonna be what we will be answering in the coming videos, is how can we find the value of D? So long time ago, people used to get the value of the diffusion coefficient from experiments. So scientists would go into the lab and have setups to do the experiments, get data, and from the data they can calculate or estimate the value of the diffusion coefficient. But this is not valid for everybody, and this is not something that we can easily do. So what we can do is simply go to textbooks and look for values of the diffusion coefficients. We already have some published data that we can use, like what we see here in this table. So what we see here is one table for the diffusion coefficient in gas phase, and this is in liquid phase. So I'd like first to focus on this for like few seconds, just to take a look at this this system or this table. So here we have system, the temperature, DAB multiplied by the P. So this is not the diffusion coefficient only, it's multiplied by the pressure, and the same for here. And here the system, it says air, ammonia, aniline, benzene, and so on. So as we said before, the diffusion coefficient is a function of the two species. It's a function of the diffusing species and the species that it is diffusing into. And from here we can understand that why air is put in this row with no information, and we have rows for the other species here. And the reason is this is the ammonia in air. So this is the diffusion coefficient of ammonia in air, aniline in air, benzene in air, and so on. So this is the solute. These are the solutes, and this is the solvent. It's a name that's being used. And this is at specific temperatures. So we know at which temperature the diffusion coefficient was predicted. The other table is nice because it gives us more information. This is diffusion coefficient in solvent, which is water mainly. There is ethanol here. And you'd see there are many systems. I have chlorine in water, hydrogen chloride in water, ammonia in water, and so on. So let's take a look, for instance, at carbon dioxide. So you'd see we have two values for carbon dioxide at two different temperatures. One at 283 and one at 293, and you see there are two different values of the diffusion coefficient, which is 1.46 and 1.77. So you see it's 10 degrees increase in the degrees Celsius increase in temperature would lead to like a significant increase in the diffusion coefficient. So this is one thing that we can understand, is that the temperature affects the diffusion coefficient greatly. You can see carbon dioxide here in water, and here you can see carbon dioxide in ethanol, and you'd see there is a totally different value. It's 3.2, and here in water it's around 1 point something. So there is a great difference between this case and this case, just because the medium is changing. One other thing here that we can notice is that, for instance, I have sodium chloride in water. We have many values for diffusion coefficient which correspond to many values of the solute concentration. So if the solute is diffusing with different initial or concentrations, then the diffusion coefficient is different. So again, this table is telling us a lot about the factors that affect the diffusion coefficient, like temperature, like the concentration, like the solvent itself. But then there might be a very common question that, or a very common case that we notice or see, that I need a diffusion coefficient, but I cannot find it in the table. I need a system which I cannot find it here. Maybe I need sodium chloride in ethanol, and I don't find it here, and I cannot find it in any other tables in literature. So this is something that we face a lot, and in this case we need to find another way to get the diffusion coefficient. So what we will do is we will use equations that have been produced by scientists who did a lot of experiments, and they produced some equations that we can use. And this is going to be the topic of the next videos. But before we talk about these equations, we need to understand one thing, which is kind of side topic, but it's an important topic, at least for me, because I believe it tells something important, is how do scientists get these equations. So the equations or the relations are got either from from a theory-based relation, or we have theory-based relations which are based on a theoretical background. There is a basis, a scientific basis or a scientific equation that is used, and then there have been some derivations or whatever until we reach the final form of the equation. And this is going to be one case that we will see in the next video, this is useful in many cases. But in some cases it's not useful. Sometimes they don't, or the results of these theory-based relations are not matching with the experimental data, and this might be because the equation that we predicted is not including all the parameters that are affecting the system, or any other reason. And in this case, scientists tend to use another approach, which is producing what we call empirical relations. And these empirical relations are relations that are produced based on the experimental results. So it's supported by experimental and observation, and not supported by theory. So they will spend a lot of time in the lab doing experiments, getting data, and then fitting the data and doing regressions and many things until they find a relation that fits with almost all or most of the experimental data that they produced or from their experiments. So why I'm telling you this is first case in the theory-based relations. They have a theoretical background, and that's why this equation must be, or the units of the parameters that are in this equation must be homogeneous. So if you're using centimeter here, then it has to be centimeter on the other side of the equation. So the units must be homogeneous. But this is not the case for the empirical relations. They might be homogeneous, but it's not necessarily, or they don't have to be necessarily homogeneous. So you can find units of atmosphere with units of foot with units of whatever inch in the same equation. So you can find something, and this is something that we will see. We will use angstrom in an equation that's producing centimeter, and this is or centimeter square per second. So this is something that is not a problem, since it's an empirical relation. So there is no constraints on the units, because the equation have been predicted using these units that are used in the equation. And that's why in these equations you will find that we will mention the equation, and we will mention the units of each term in this equation, because these are the units that must be used in this kind of equation. So what we're gonna do in the next videos until we finish this chapter is to discuss the equations that are or there's some of the equations, or some of the most famous equations that have been produced to predict the diffusion coefficient in gas phase, in liquid phase, and in solid phase. We have many equations. It's important just to know what is the system that this equation, or each one of these equations, is suitable for, because there are differences, and some of the equations will be good for systems and not as good for other systems. So and that's why we have many systems, because some are good for systems that others are not. So it's important to understand which is which. This is for gas phase, for liquid phase, and for solid phase. Again, I would like you to keep in mind the relations and the influence of each one of these parameters on the diffusion coefficient, because this is pretty important. So in the next video, inshallah, we will start talking about the gas phase diffusion coefficient, or the equations that are used to predict the gas phase diffusion coefficient. So I'll see you then, inshallah. Goodbye.